Welcome back, and welcome also to our colleagues online to the last component of this LMS General Meeting 2026. And so I'm delighted to welcome our second speaker today, Tristan Buckmaster, for his lecture on computer-assisted proofs in fluid PDEs. Tristan is a professor of mathematics at New York University, and he earned his PhD from the University of Leipzig in 2014. His academic career includes a postdoctoral fellowship at New York University, faculty appointments at Princeton University and the University of Maryland, and a visiting position at the Institute for Advanced Study. His research explores partial differential equations and fluid dynamics, with a particular focus on singularity formation and the non-uniqueness of weak solutions. In 2019, he was co-awarded the Clay Research Award for his breakthrough contributions to the mathematical understanding of the Navier-Stokes equations. Please give a warm welcome to Tristan Buckmaster. Tristan.
Well, thank you very much for the invitation. It's a pleasure. It's great to be back in. I think last time I was in Edinburgh was about 20 years ago, so it's been a while. So yes, we'll sit. So I just want to talk about like bits and bobs of different things that are in my research, and I think, I mean, Kevin gave a great talk at the last talk, and there'll be some things that there'll be a lot of things that connect to that talk. And I also wanted to just say that things are moving so fast that I think it's important to share like techniques, workflows, and things like that you would never think of. You know, when Fermat's last theorem was proved, he did it alone. He sat. But in today's society, everything moves within 6 months or a few months. And I think it's really important to share how you're interacting with sort of these new innovations and so forth. So anyway, recently, my main research has been related to self-similar solutions. And so to give a concrete picture of what self-similar solutions are, so this is just for the Burger's equation, which is one of the simplest nonlinear PDEs. And in this case, the singularity happens in that the gradient goes to infinity. So what makes it self-similar is if you this blue curve over here is the original solution to the Burger's equation. Now, if you take this red box and you stretch it back out to this box here, and this is the same blue curve, but it's the blue curve within the box. And what you see is that while something is going to infinity, in this case the gradient, in these new self-similar coordinates, everything is converging to something nice and smooth. And this makes it a tractable problem to study with analysis. So here's this simple example again. Here's Burger's equation. So U is the velocity, and we make this self-similar ansatz. So we have this new y. This is the y-axis, and the x is the original coordinates. And you see that the entire singularity is now thrown into the change of coordinates. So the change of coordinates is what's singular. So this time the singularity is happening at time 1, and so the change of coordinates is actually singular. But once you transfer to these new coordinates, the solution you get is perfectly smooth. And so this u here is the solution. This orange curve is what it converges to at the time of blow-up. And what I should say here is that in these self-similar coordinates, it really describes what happens to the fluid at the time of the singularity and just at the point of singularity and not anything else. So that was somewhat a misunderstanding in some of the PDE before, was that the self-similar solution had to sort of have a global picture. But in these fluid problems, the self-similar only really describes at the point of the singularity, at the time of singularity. So you can see a singularity. So in undergrad, you learn in undergraduate PDEs, the Burger's equation is one of the first equations you study. And you can see a singularity happens by taking a derivative of the velocity, and then you follow characteristics. So u stays constant along characteristics. And then you see that you get this Riccati equation, which flows up infinite. And it just depends on how negative the gradient is. Okay, so after doing these change of coordinates, you get left with this new equation. This new equation has this velocity u, and it has this self-similar parameter lambda, which parameterizes the sort of self-similar scaling of the solution. And so instead of trying to find something going to infinity, you're trying to search for some solution to a PDE, smooth solution to a PDE, and you also have to find the self-similar parameter. Now, for the Burger's equation, everything is kind of explicit. So this is the implicit solution to the equation, and one can check that if you want this to be globally defined, then you need that this, first of all, if you want this to be smooth, you need that 1 plus 1 over lambda is a integer. And that's why are we interested in this problem? These are just sort of general problems in the whole, the general, the big problem in PDE is whether solutions exist for all time, smooth solutions exist for all time for the Navier-Stokes equation. And the current thinking is that they don't, that singularity will happen in finite time. So, the end goal in one of the big goals in PDE is to prove that a singularity for the Navier-Stokes equation happens in a finite time starting from smooth initial data. So, so if you want this to be smooth, you need 1 plus 1 over lambda. And you want it to be globally defined, you need this to be odd. And then you get left with these different lambdas. So lambda, you get a whole sequence of lambdas, and they all correspond to different self-similar solutions to the Burger's equation. And for the first one, you can actually explicitly write what it is. So this is the so-called stable self-similar solution to the Burger's equation. And what does it mean by stable? It means that modulo a finite number of symmetries of the equation, the type of singularity is stable, that it will converge in these coordinates to this solution. And this might seem like completely, I took one of the easiest PDEs out there. It's like maybe a trivial sort of statement, but this PDE describes shocks. So shocks we see all the time, and this describes what the formation of the shock, so the behavior of the air, or when a shock forms. So this is something actually physical, and this actual solution here describes something that's physical. Okay. So now I want to. So I brought the. Sorry, I want to go back one slide. So one thing I want to say was that. So this is. I said this was stable. What do I mean by this being stable? So I said that it's stable modulo the symmetries of the equations. But another way of formalizing that is you write this as you linearize around the PDE. You write the linear operator, and you look at the spectrum, and you see that the only spectrum lying in the positive plane, positive half plane, is the ones corresponding to the symmetries of the equation. Okay, and so I reduced the problem to finding these smooth solutions, and then you have to prove some sort of stability. That's the general strategy for proving blowup. So this was just a video I took yesterday at Portobello Beach, where I happened to see a mathematician writing on a blackboard, and I was thinking that in the So yes. So I want to describe how we can use computers defined. So that was a particularly simple equation where I can explicitly write down the solution, but in general, these solutions to these PDEs will be, they may not look particularly complex, but you can't write them down with sines or cosines or simple expressions. And so you have to find them numerically. And then you have to somehow, how do you turn something which is numerics into something which is a proof? So this is, so one of the big results in PDE in the last few years relates to this so-called Liouville scenario. And so this is the Euler equations, which is basically Navier-Stokes equations without viscosity. And this is in the case of the Euler equations inside a cylinder. And actually, I mean, the diagram looks like it's from outside the cylinder, and the proof is exactly the same outside the cylinder. So I'm going to say it's outside the cylinder. But anyone like looking at this, I think that looks like the fluid is outside the cylinder, but maybe the authors meant something else. But because it's self-similar, it only describes the behavior at really just the self-similar profile describes the behavior at the point. It actually doesn't matter if it's inside or outside the cylinder. It just matters that there's a boundary. So there was compelling numerical evidence in 2014. So just this is just after I got my PhD, or why I hadn't just before I got my PhD, and just recently it was proven by Chen and Howe in a sequence of papers that there exists smooth additional data to this particular problem. So it's like Navier-Stokes without viscosity, where there's a boundary. Okay, so how you go about this problem is actually, so this is the original problem. So this is not the original one. This is the 2D Booth-Ness equation. And why are we looking at a different equation? The reason is that the world is flat in the sense that if you zoom in on the cylinder looks flat. Okay? And so what actually you can do a little bit of analysis is you can see that it's a leading order. The singularity is described by the 2D Booth-Ness equation on the half plane. Okay, so then all you have to do is you apply the same trick, right? This is in self-similar coordinates, you get some other equation. And if you can find a self-similar profile to this equation and then prove some stability, then you can prove blow up to Euler. That's the modulo some decaying terms which you deal with via stability. Okay, so we started a group of us, Yonji Wang, Yao Lei, and Javier Gomez Serrano, started this work on using neural networks to find the solutions. And so how a neural network's used is actually pretty simple. You should just think of this neural network as a different basis. So your typical basis that you're used to is a Fourier basis, which is a linear basis. So you replace that linear basis with a nonlinear basis. So you have something like your linear basis, and then you compose it with another one, and you compose it with another one, and compose it with another one. Each composition is a layer, and you could think of the individual layers like linear basis. So it's just a more complicated basis. Okay, and you train. So this new basis will describe the solution. And the purpose of using this complicated basis is that you can describe this solution with a small number of parameters, which makes the search space more dimensional. So you're looking for all these weights, and this just describes the solution. And then how do you know? So this just describes some random function. How do you know you're getting closer to the solution to the equation? Well, you just put the PDE. So this is a smooth function. then you can evaluate the right-hand sides of the PDE, and you can use that to train the network and to get better weights. And so this is what we did. And then one question naturally is, so how do you, so this is how you train for these equations, but then how do you train for this lambda? So the lambda is this self-similar parameter. Well, the smooth solutions only exist on discrete lambda. So if you select a small window of lambda, then if you choose the wrong lambda, you'll get some sort of spike because you can't approximate a non-smooth function by a smooth function very well. So you get a sort of spike in the error. Now, just to sort of link this in, and how does this sort of fit with sort of like Navier-Stokes and so forth. So this is just a toy model. This is a 1D equation called the Cordova-Fontellus equation. This is father and son. So this is just a toy model, and you sort of model viscosity by adding this term, and depending on how you choose alpha, you can sort of model between sort of an Euler model and a Navier-Stokes, make the viscosity stronger or weaker. Now, if one does sort of this self-similar equation, and I also introduced some sort of self-similar time, which just stretches out time to infinity, then what you see is that this viscosity term has this new term, but it scales differently than all the other terms. And if the self-similar parameter is chosen, if you can find a solution with a self-similar parameter with the right inequality, then you can make sure this term decays. And so you can sort of treat viscosity as an error. And that's also a common theme in my research. So the thing we got the Clay Prize for was when we proved non-uniqueness for the Navier-Stokes equation, was basically saying viscosity doesn't matter. Okay, if you in the right regime, viscosity doesn't matter. But the key thing is you have to make, in this case, you have to make lambda sufficiently negative. And so we know by sort of pen and paper that a blow up occurs for alpha between 0 and 1.5, and you have singularities. And you have smoothness for alpha greater than 1, and then it's not known what's in between. Now, to address the open range, you'd need lambda less than 1. Now, it turns out for the stable case, which is this stable CCF solution, which was previously known, lambda is actually greater than 1. And so then in the collaboration, so with the original authors, along with Gonzalo Calabora and DeepMind, we were able to find some more solutions. So using training these neural networks, and so we were also able to find a whole bunch of solutions that weren't known. So in our original paper, we found the self-similar solution to the Boussinesq equation, and in this later paper, we showed all these green solutions, and then in a more recent paper with the subset of the authors without DeepMind, we also found with the fourth unstable solution. Okay, so these are solutions that are incredibly hard to find by traditional methods because singularities are forming. So the traditional way that you would find them was that you would evolve a PDE in time. And this is how the original Hao-Le solution was found, or it was conjectured. You evolve it in time and then you zoom in. But all these solutions, which aren't the first line, are all unstable. So you modify the initial data just a tiny bit and it won't converge. So you can't observe them with traditional sort of evolutionary numerics. It's impossible. Okay, because the smallest chain, and you can also see that as they become more unstable, you end up having these sort of strong gradients that form, and like there's no way to sort of tune things such that you could evolve to find these singularities. And that was the traditional way that people look for singularities in these equations. In this sort of new method, you just look for it directly and you don't care that it's unstable. I mean, it makes it still harder when it's unstable, but because you're searching for it directly, the self-similar profile, you don't actually mind that it's unstable. Okay, so we found a bunch of these solutions. So this is all just sort of, and this is the later paper where we, this is the later paper where we, not only that we found that, what does it mean that we found this solution? The error, this is the right-hand side, the error is to machine precision, or it's to the same order that you expect from round-off error for doubles. But, so if you wanted to use numerics that go better, you would have to convince NVIDIA to create registers quadruple precision, which so far they have not complied with. They're more happy with 4-bit or 8-bit precision. But yeah, that's another story. Apparently, mathematicians are not on the highest priority for NVIDIA. So the next question is, how do you take these these are still numerical solutions and turn it into actually a proof? And so you get a robot to write things down. So this comes back to the computer assisted proof, which is the subject of this of these two lectures. So first you identify some self-similar profile, and you don't have to use neural network, so you can use whatever numerics you want. Then you have to rigorously bound the residual of the equations up to some acceptable error, and I'll talk about that in a few slides. So these errors here are still just evaluated with regular floating point arithmetic. They have no sort of certificate that these are the actual errors. And if you tell a numerical person that this is the errors 10 to the minus 14, they just won't believe you actually. Because they'll believe that you're probably not taking into account some round off errors, or there's little spikes in between that missed, etc., etc. So, but anyway, it's not a proof. So, but you have to rigorously bound these errors of these equations, and then you have to then when you just have some approximate solution to the self-similar equation, but not but you need more than that. You need to prove some sort of stability in order to prove blowout for the actual original equation. Or alternatively, you have to show that you could think of it as some sort of infinite dimensional implicit function theorem argument or inverse function theorem argument, that you have an approximate solution. There exists an exact solution nearby. And so one of the key ingredients we use in these arguments is that we have this linear distributivity estimate. So if you take the linearized operator around the solution, then you have a sign. The operator is a dissipative modulo some finite rank operator. And so that's a key ingredient. And then you have to analyze the finite codimensional stability. and you have to establish rigorous bounds on all the remaining terms. Okay, so in order to so just to check, just to sort of to check that you can sort of if you think of it from this like infinite inverse function theorem argument, you want that there's only a finite number of you certainly don't want you certainly just want one eigenvalue at 0, which you can remove with symmetry, but you want to you need to prove this modulo a finite unstable manifold, and so you want a finite number of eigenvalues on the positive real half plane of the spectrum, and this part is just junk. So this is numerics of the linearized operator for the IPM equation. Oh no, this one is for the for one of them. Self-similar. I think this one's for CCF actually. Yeah, and so so we want to bound such a thing, and you have to do more than that. Just the operator is not self-adjoint, so you can have transient growth, and you have to bound all this possible transient growth. So you, in order to show that you're close, that you can basically invert the operator, you need bounds on the transient growth. You need to have the bounds on the spectrum, and you need to put that all together. And it has to all be. You have to actually say numbers, rigorous numbers. Okay, and so that was for CCF, and this is for IPM, and this is just this is an eigenvalue from the symmetries 0 and 1, and this is a one-bound stable. And this is for the stable, the first unstable, and this is for the second unstable. Okay. Now the first question is why the all-important estimate that you have, that this is kind of the important estimate you need, that if you the first thing is you do numerics and you find a very precise self-similar solution, and then the second check that you're on the right track is that you check the spectrum and you check that there's only a finite number of positive eigenvalues, and then the third step is that you have to check that you have some sort of linear derivative estimate. And if you've done all that, then you just wait 3 years and 300 pages of math, and you'll have a proof. But at least you know it's worth writing those 300 pages of math. Or maybe it's, depending on it. Right, Once you have this sort of estimate, you kind of know everything. You know it's going to be very painful, but you know eventually it will. There's a whole program of what to do next. Okay, so let's consider for the very simple example of the Burger's equation that we had before. Why do you even expect such an estimate? And the reason is quite simple. So the estimate depends on the space you're dealing with as well. So if you deal with a Sobolev space with enough derivatives, then you get a sign. So basically, the non-compact part of the operator has a good sign, and then you can swallow the compact part in the finite rank operator in that S. And so the reason, so for the Burger's equation, so this is the linear operator associated with Burger's equation, and essentially, when you do an energy estimate and you differentiate this term enough times, you get this 3-on-2 factor that comes out, times the number of derivatives, and you have a lower bound on the derivative of u being greater than -1. And so every time you take a derivative, you essentially gain at least a half. And so eventually you get a high enough. You get it. If you take the right space, you get this distributivity estimate. Now it's more complicated for other equations. For CCF, when to get a good sign, you have to introduce a weight. But all this is sort of we know what to do. Okay, so that now getting on to interval arithmetic. So how do we turn all this into rigorous math? So we want to do rigorous numerics. So interval arithmetic is rather simple. Instead of your traditional arithmetic acting on real numbers, they act on an interval. So you think of every number being an interval. So let's represent the width of the interval as a power of 2. And so you should think of this as like 5 plus or minus some number. And then when you, it's pretty easy to do this calculation. You have to round up. Okay, so if you add these two numbers together, you get 8 plus or minus 2 to the minus 3, where I'm rounding up the error. And this is such a simple concept, but then you can take you can turn this into rigorous proofs of estimates of infinite dimensional operators. You can turn these are very simple arithmetic operators, but a lot of things can be built off them. Okay. And so this is just to give a simple example, is say you want to go to this original question I had where let's not prove the entire pipeline proving that there exists a singularity, but let's just do rigorous numerics. So say you have some approximate solution to equation and you want to say that that it satisfies the equation up to a specified error, and you actually have to say what that number is. Okay. And I should point out that for an analyst going into the world of interval arithmetic is super painful, and I'll talk about this on the coming slide, is that for an analyst, I'm so used to in all my less than equals to the little wiggly line underneath the less than equal to, which involves a implicit constant. And I never say what that implicit constant is, and it changes every single line. And then to go into the world of interval arithmetic, where I have to say what every single constant is super painful, especially if I change one constant, then it changes all the constants that go after. So I'll talk a little bit more about this. So let's consider this very simple problem. We're not interested in showing singularities. We're just interested in saying we have some approximate solution to an equation. Can I rigorously bound the error? So when I give a talk to numericists, that they will actually believe me when I say the error is 10 to the minus 14. Okay, so this is joint work with Mikhail Shavit and Yonji Wang. So in this case, we're looking at steady water waves, steady gravity compatibility water waves, and you can do a clever transformation, conformal change of coordinates, where such stationary water waves are described by a modified Babenko equation, which is given by this. It's not so important the physics involved in all this. I just want to, this is some equation that we can find approximate solutions to. So H here is the Hilbert transform, the periodic Hilbert transform. and all the subscripts are derivatives. And u is this conformal coordinate, and y is the height of the wave. Okay, and you have you have these parameters like mu, which is the wave speed, and beta, which is the surface. And so we suppose, because it's a periodic solution, we approximate it by some cosine series. And the goal is to determine a epsilon which bounds the right-hand side of the equation. We plug this into the equation, we get some right-hand side, and we want to say that over the whole domain, this error is less than epsilon. That's the goal. How do we do that? Okay, so this is it's also really great this talk came after Kevin, and so I'm a recent convert to lean, like, and this also has to do with the last slide, or the last couple of slides of Kevin's talk, is that a lot of doing analysis in lean was difficult, and because basically a lot of analysis is just not in MATLAB. But now we have things like Fable, which can actually just write all the stuff that we need. Okay, so this is like super recent sort of, and I was sort of inspired by this sort of workflow, but I also work by Scott Armstrong. So I should say, and this also, I mean, this parallels a lot with many things that Kevin said in his talk. So one drawback of interval arithmetic is it involves like a multitude of decompositions and explicit constants throughout. So basically, you have to turn something which is essentially an infinite dimensional problem and turn it into a finite computations of adding things and subtracting things together. You know, and this involves a whole lot of decompositions, a whole lot of actual constants, and there's a question is that you write, you know, you have your paper where you have all the main analysis is in your paper, and then there's the interval arithmetic part of the paper where you say that the error is less than some amount, and then there's the question is, how do you present interval arithmetic? Like, I could give you, the referee, tens of thousands of lines of code, and you can see by that, you know, the paper that was submitted to the annals, some referees don't like that, right? And it's painful for a referee to go through tens of thousands of lines of code and check that in those lines of code, you've done all these decompositions correctly, and you haven't missed a factor of 2 somewhere in thing. And so this is actually a real problem in the interval arithmetic community, is that you submit your paper along with a whole bunch of code, and then often it's actually quite common that the editor will assign different, one referee just to deal with the main paper, and another referee just to deal with the interval arithmetic portion of the paper. And you can write it in different languages and all sorts of things. So it's actually, especially when the for simple problems, so we have another paper where you do interval arithmetic, but it just amounts to proving positivity of some high dimension of some high degree polynomials. You know, that's not like super strenuous for a referee to check, but in the case of these ones, there's really, you know, there's infinite. You have to deal with the Hilbert transform in this specific example, but in high dimensional problems, they also just, the lines of code is just, it's very, it would be, I wouldn't personally, I wouldn't like being the editor assigning someone to referee such a paper. So how can we make things a little bit simpler for the referee? So one one sort of proposal, and this is sort of just sort of, this is in the spirit of saying that this is sort of new ideas that that I've had in the last sort of few months, whatever, and it's back, and it's only possible now that we have these new models of LLMs available, is that you have that you can split the argument into two parts, where one, you have traditional interval arithmetic, and that's done with there's a library which does the interval arithmetic. So I use R, but there's other libraries available. But there's you have that, but you also have another set. You have some lean code which certifies all the algorithms that you have in the interval arithmetic are correct. You have that all the decompositions that you have done are correct, all the constants you've done are correct, and then you link sort of the two together. So in this way, and the thing, with lean, the thing is you don't have to check all the lean code. You have to check that the definitions and the theorems are correct. So this would make the referee's job less arduous, and it's not one thing a big thing people one thing people have been saying about using lean is that it's good for checking that a proof is correct, but it's more than that. It's really good at checking what you're doing at this moment is correct. So in your current actual workflow. So when you're writing your interval arithmetic, you want to actually check that what you're doing is right. So it's not just for the referee, it's for the author itself. Okay. So this is just a little thing. And so, okay, so then I want to go back to how do we use interval arithmetic to say, show that a PDE on a periodic, so in one dimension, say, a periodic domain, an approximate solution has a certified error. And so one thing you can kind of imagine is that you have this like cosine series, right? You can plug this in. Okay, if the Hilbert transforms the Hilbert transforms, some of the Hilbert transforms are fine, but like you could sort of figure out how to do it. There's other ones which are not fine. You can kind of figure out how to do it by hand, how to work out what the error is on the right-hand side. Okay, you know what the derivatives of cosine are, and you know what the Hilbert transform of cosine is. So you can evaluate this equation at a finite number of points. Okay, and you can quite easily see how you would do that with interval arithmetic using just the symbolic relationship of how you take derivatives and how you take the Hilbert transform of the cosine series. This term is a little more difficult, but we'll talk about that in a second. Okay, so and then it's really quite easy. So the basic idea is a simple estimate. A Lipschitz estimate is you know what all the coefficients of the approximate solution is, so you have some bad bound on the Lipschitz norm of the solution, and then, or the Lipschitz norm of the right-hand side, let's say, and then you just bound it by in terms of the evaluations at a finite number of points, and in terms of the Lipschitz norms and the distance between those points. And then easy generalization is that you do a higher order Taylor series at each point. And this way you can get a rigorous bound on you can actually say that the error is less than some specified epsilon with interval arithmetic. Okay, so then how do you do something more difficult? So how do you deal with this term where we can't sort of easily symbolically write down what the right-hand side is? So if this was a numerical, how you do this numerically is you'd use the discrete Fourier transform, the fast Fourier transform numerically, and you would you would use that to approximate the Hilbert transform. And there is a interval arithmetic version of FFT. And of course, there's an alias error from taking only sampling at a finite number of points. But you can bound that, so the Fourier series that you get from the discrete Fourier transform is not the actual Fourier series. You have this extra error from the higher. You have this extra aliasing error, which you can easily estimate in terms of the derivatives in terms of the bounds on the Fourier series itself, which come from the derivatives of the solution, or the derivatives of the right-hand side, which you have some bad bounds for. And in this way, you can take the Hilbert transform of this complicated object, and you can turn it to a finite computation of doing a interval arithmetic version of the FFT, and then you can bound all the errors, and you can take n to infinity and make these errors as arbitrarily small as you like. So really, it's none of what I've said is particularly deep. Okay, and this goes back to why I'm also suggesting of using lean for such processes, that lean and LLM. Why I'm also suggesting using LLMs to help do interval arithmetic and lean is the fact that much of this work is like very tedious and not particularly deep, but needs to be done to turn it into a proof. And this is the kind of stuff which is perfect for the LLMs of this generation. Like, I'm not asking the LLMs to do something particularly creative. I'm asking it to do something which is very monotonous, and they're quite happy to do it as long as I give them a subscription every month. Yeah, and so there's a lot of what I want to say about this is that there's a lot of things out there in the world of PDE where it sort of broadens our horizons, because we were stuck, like if they're in these, like in examples like the Navier-Stokes equation, this existence of a singularity for the Navier-Stokes equation. If you're trying to prove that with pen and paper, like, it's like, how are you even meant to like begin if you can't write down what the solution looks like? Like, the solution can only be described by a computer. So you need this sort of bridges some of the gap. It also allows us to do some things that numerical people could do, but we couldn't trust them, and they didn't trust us. And so this allows us to like bridge that gap from what numerical people could do to what we could actually prove. And with the onset of all this new technology, we can actually bridge that gap. So, questions?
Time for some questions.
I was wondering if you can expand a little bit more on what you just said, that bridging the gap between one numerical computer and one not.
Yeah, so I mean, like if we just go back to this this problem here, like there exists a singularity to the Euler equation with infinite time in the case of the boundary. There's no way to go about this, no known way to go about this equation, go about this and proving this with pen and paper. You need to have some sort of approximation of a solution at hand. And now, like in some traditional PDEs, you could show that for some simple PDEs, you could show that with pen and paper, there exists some solution at pen and paper. But in these kind of cases, you really need a candidate. And so you need a self-similar candidate solution. And then basically you need to show that there exists a real solution nearby, this sort of infinite dimensional implicit function argument. And this is what the analysis plus this interval arithmetic is what bridges that gap, allows you to do this sort of infinite dimensional inverse function theorem kind of argument to get from this approximate solution to a real solution. Now you can think of it for any sort of PDEs, like any sort of like stationary solutions to things or periodic solutions to things. There's some cases that you get lucky and you can use pen and paper and just show that they exist. But in many cases, there's no way to really go about them pen and paper. You just have to actually find them. And then once you find them, they have to actually show that they really, like you find them numerically, then you have to actually show that exists something nearby. So you bridge the gap in the sense that now we're not just left with proving what we can only do with pen and paper, we can also prove what the numericists can do. We can turn what numerical people can do into actual proofs. So that's the gap we're bridging.
Then numerically, you give your first candidate.
Yes.
And then you do the rest with the.
And then the rest is to turn using interval arithmetic in order to turn that candidate into an actual solution.
I actually have a follow-up question, or maybe I will ask later.
Daniel.
So when you said at the end, you described the solutions are described by a computer, you were referring to numerical solutions.
Yes.
I don't know if you exactly said this, but so this includes things like numerical, the solutions provided by classical numerical methods, for example, finite things and things like that.
Exactly. So you start with, it doesn't have to be a neural network. There's nothing special about, it was just that we found these neural networks particularly good at finding these unstable solutions, but you could use classical methods to find your candidate solution. And then all you have to do is represent it in some symbolic basis. So some like, you can think cosine, sines, but whatever your favorite basis is. And then all you're left with is a finite number of numbers, right? What are the coefficients that come out in front? So actually I should say that when you find something with a neural network, you don't leave it in that neural network form. You rewrite it in a linear basis. So once you have you found it with this complicated basis, you don't want to use that for a proof because it would be a complete mess. So you actually then re-express the solution in a nice linear basis, which you can do analysis with.
The numbers you find, are they just rational numbers with relatively small?
They're just numbers, yeah. They're just rational numbers. And then then you just say, you write your linear basis up to whatever, 1,000 different coefficients or whatever, and that's the input to the interval arithmetic. So you say that's your approximate solution, and then given that approximate solution, you do all the stuff that I said before, just say what the error is.
Sorry, so the interval arithmetic is exactly what gives the error, is that what you said?
And other things, like I gave you the simplest thing you could do with it, which is to find the error. But like in reality, there's a lot more that you have to do. You have to basically make this whole inverse function theorem argument rigorous, and there's a lot of things that you have to do in that.
Kevin, maybe one last question.
This is a slightly weird question. So the real numbers that I see in the Langlands program, they tend to be eigenvalues of differential operators. And sometimes number theorists might decide to work out what they are to 1,000 decimal places, just to see if they can or see if they can spot. So you were quoting eigenvalues to 13 decimal places and then saying, actually, we can't go any further. Is there a theoretical, can you take these things Could you do something theoretically and actually work out these things to
Well,
effect?
I mean, what we do is that, so I mean, we don't use those. I mean, what we do is we have the values that are showing the actual solution, and what we, I mean, it's we say that all the,
You're not
we say
interested in lambda, you're interested in
but we say that the error is like 10 to the minus 14, and then we say that there exists an actual solution nearby where the error is 0.
yeah.
So so you take something. First of all, you say that the error has to be 10 to the minus 14. That's the first stage, and then you have to do a second stage, which is to show that, like, if you think of it just as a matrix, you can invert the matrix or whatever and find an exact solution nearby, in an infinite dimensional way. I mean, that's essentially what you're doing. Okay, but it's of course, it's not that easy.
Yeah, I think that's a good place to stop. So let's thank Tristan again for